9.5 is permutations and combinations. Raise your hand if you've heard of one of those before. Audrey has it. She took it from me. You've heard it from in music? Really? Very interesting. All right. Permutations and combinations are a concrete formula, too. Just like expected value. I don't know if there's quite as much ambiguity in it, but they're all related to the idea of a factorial. How many of you have seen a factorial before? That's the exclamation point that's up there. Okay, I've got to go both directions here. Let me tell you what a factorial is. When I see n factorial, what it means is n times 1 less than n and 1 less than that, and you keep going down until you get to the number 1. So if you're talking about 10 factorial, it means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 1. That's what factorial is. Okay. By definition, we need to say what 0 factorial is, because obviously 0 can go down to anything that's already below where we're supposed to be going down to. 0 factorial, by definition, is the number 1. And we're going to try some. Okay, so the first one we're going to do is 4 factorial. So again, what that means is I multiply 4 times 1 less than 4 and 1 less than that until I get down to the number 1. And then I either multiply my head if the number is small enough, or I grab a calculator and factor the negative or whatnot. And I multiply 4 times 3 times 2 times 1, and what do you get? Say louder. 24. So 4 factorial is the number 24. All right, the fundamental principle of counting, and this is actually earlier in your textbook. We don't hit it very hard in that one, but it does come up in chapter 2 in your textbook. It says the following: if an event M can occur in little n ways, an event capital N can occur in little n ways, then event M followed by event N can occur in M times N ways. And we usually see this with ways of doing things. Like, for instance, if I have 5 different shirts and I have 6 different pairs of pants and everything matches. Okay, so we'll worry about that issue for women, and that's what we do. Aside from the matching issue, how many different outfits can I create? Well, I have 5 shirts and I have 6 pairs of pants, and I say 5 times 6, and there's 30 outfits. They may not all look extremely different, but they're all different, technically different outfits. Okay. Do you guys remember Sonic doing something? It's been a couple years ago, right? They talk about the number of drink combinations. This is what they did. The number of ways you can choose any of their beverages with no add-ins, the number of ways you can choose them with 1 add-in, with 2 add-ins, and 3 add-ins, and it doesn't math the problem. And I assume if you put everything all together, you probably have something called suicide. They know by suicide. My brother used to do this in the fountain drink, right? Some people do it still in the GC. I've seen them. And they just put their little drink in every single slot, and they get a mixture of, yeah, I don't know. But, okay, so here we've got an example. Here's Pizza Planet. Do you know what Pizza Planet's from?
That's what I was thinking.
No,
I was like, this is a real place.
There actually is a Pizza Planet in Oklahoma City. Saw a great one for it yesterday. Thought it was crazy. Had to send my husband a text message because that was so funny. And so Pizza Planet offers 3 kinds of salad, and it's not 15 kids. It's 15 kinds of pizzas and 4 desserts. And the question is, if you can make a meal of 1 salad, 1 pizza, and dessert, how many different meals could you make? And this is a really straightforward problem. What do you have to do? Right. You multiply 3 times 15 times 4. 3 salads, 15 pizzas, 4 desserts. And if I multiply this together, what do you get? 20. So there's 180 different meals, quote unquote, that you could have at Pizza Planet. Now, a permutation is along the ideas of the Sonic example. Okay? So permutation is, in fact, actually the next one's even more, but it looks like this in the notation. So the N and the R both look like subscripts. They're down lower than the line. It's not just a lowercase n and a lowercase r. They're actually subscripts, okay? One is a subscript before, the other is a subscript afterwards. The formula, though, looks like this. It's n factorial over n minus r factorial. Okay, so we're going to do a problem. It's not as complicated maybe as it looks. But here's the deal. This is the number of ways that if you have n choices to make, and you want to choose r of them, that's how many different choices you have. Okay, so this is the whole idea that you're at Subway, and they've got all the vegetables, and they've got 15 different vegetables there. And how many ways can you choose 3 different vegetables? Okay, so this would be the idea. And some restaurants do this, right? You can add a certain number of items as side items on each burger or something like that. How many different ways can you make those choices? Now, the one thing that is not true about what all I just said is that the order wouldn't matter, right? It doesn't matter at Subway if they put the onions on before the lettuce. This doesn't matter. With permutations, the order does matter. Okay? There are things you do in life that the order matters. It matters whether you put your pants on first or your underwear on first. Just saying, right? It's not going to work if you put it on the wrong order. My son has tried this before, right? Okay, this is the kind of stuff kids do. The order matters on this. So here's an example. So 50 people show up for a game show. 2 of the people are selected at random to participate. This sounds an awful lot like Who Wants to Be a Millionaire to me. Okay. Huh? Do you guys know what that show is? Yes. Okay, good. Fabulous. I'm not too far back in time. How many different ways can this happen if the order matters? So the order might matter in this case, for instance, if let's do there a good example. This is the one I had. There's the one they compete against each other. We easily had a whole bunch of people competing against each other. The Are You Smarter? 5th grader, I think, does this. I think there's 2 contestants at a time. Maybe there's not. Watch some of them. It's a different person. Yeah, that's true. I can't remember the show. Don't know me. Oh no, it's old. What's it? It was Paul Barker.
Oh, Price is Right.
Price is Right. Price is Right matters, right? It matters whether you're chosen first or whether you're chosen last because you have more options of actually being able to get on the floor if you're there. So agree? It matters, right? It matters a little bit in which order. So it doesn't really matter if you're the first one or the 4th one, but it does matter if you're the first one or the 7th one picked. Much of the Price is Right. All right, anyway, moving on. 50 people show up, 2 are selected at random. The order matters in this case. And maybe it simply matters for this game show because it determines who gets to go first or pick something or whatever, but the order matters. So the number of people is at the end. Okay, so this is 50 people. And it's a permutation because it says the order matters. Okay? And then I select 2 of the people. So maybe I select them out of a hat or something, but I select 2 of them in some way, shape, or form. So I expect to see the 50P2 written on the paper. And I expect to see what you have next written on your paper as well. So this one says then that this N right here shows up on top. So that's the 50 in our example. And on bottom, I'm supposed to have N minus R. So you can either write out the 50 minus 2 in our case, or you can tell me in a separate step or in that first step that that's 48 on bottom. Please not be tempted to cancel out the exclamation points. That is not a property. Okay. Do not be tempted to simplify 50 and 48. Also not a property. Okay. But what you can do is this. You can write a few of these 50 factors out. This should be 50 times 49 times 48 times 47 times ... So pause with me for a moment and I'll show you what this really should look like. This is the thinking. 48 would be 48 times 47 times ... You're ahead of me. Yes, that's on the right hand. So I really don't need to write out 50 all the way down. I really only need to write it out exactly as far as Sarah just said. I need to write 50 times 49 times 48, and I stop with the exclamation point because that tells me it keeps going. And the 48 with the exclamation point on bottom telling me that it keeps going. And then it is a property that I can cancel these out because they match exactly. So I can't factor cancel them because they have factor in common. But I can cancel them if they're exactly the same. And now they are. So now it's just a matter of taking your calculator and multiplying 50 times 49. What's 50 times 49? 2450. So there are 2,450 different ways that we could select 2 of our participants from among 50 that came in and applied and wanted to be selected. It's a lot. It's huge. But part of the reason it's so big is because the order matters. All right. Now, sometimes when you talk about permutations, the objects are not all different. So our candidates, right, our participants, or whatever they were in the last case, our game show possibility, or whatever, they were all different people, right? Now imagine that you have a bag of candy. Take your favorite M&M's, Reese's Pieces, I don't care. Jelly beans, Skittles. It doesn't matter if I pull out a purple that was at the top of the bag or a purple is the bottom of the bag. It tastes the same when I stick them in my mouth, right? They're indistinguishable. So sometimes, even though the order matters, because it's different if I pull out a red versus purple, it doesn't matter when I select all of the objects at once. Right? If I actually am looking at all the objects at once, if I pick the purple that comes first or the purple that comes last, it's no different. So these are like objects, okay? So if I have n elements, again, R1 of which are alike, R2 of which are alike, and so forth, they're indistinguishable, like my candy, my jelly beans, my whatever. Then the way that I find this permutation is I do n factorial, just like I did before, but instead of the denominator, I do R1 factorial, R2 factorial, for however many R's I have. That's a factorial, doesn't look like one. And all the way up till whatever I have. Okay, wherever it is. Wherever it ends in, but wherever it is. I don't know. Your book doesn't give it a notation, actually. So if you want to put a P, that's fine. But your book does not actually give it a notation. And I will tell you, this is the only book that I've had that gives this description, which is really good because there are cases where this actually makes perfect sense. Now, my example 4 seems like a very contrived case, and I agree. History, I can look up. Okay. If I take the word Tallahassee and I rearrange the letters, some of the rearrangements would affect the problem, right? If I switched 2 of the S's, hold your britches, have you changed, right? And it doesn't matter, right? But if I switch the T and the E, then it does matter. So we want to actually figure out how many different changes would actually affect the way the word looks. And so what we kind of figure out is how many different letters we have and how many of them there are. So there's 1 T. How many A's are there? 3. How many L's are there? I'm just going in order. There are 2. A, H. H is next. How many H's are there? 1. And then I've got A again, and then I've got S. How many S's are there? 2. How many letters are there? Oh, I forgot E. I'm sorry. How many E's are there? 2. All right, then how many letters total are there?
6.
No, not different letters, but the actual letters. 11. Count them each individually, even if there are repeat letters. There are 11 different letters in the word. So the way I find the permutation, we'll call it P because I know Sarah wants to have a letter in front. Something that says my finding. That's okay. I'm like that too. So we have 11 factorial on top, the number of letters. And then each one of these numbers that were each of the letters individually is on bottom with a factorial. So I'm going to write them all out. 1 factorial, 3 factorial, 2 factorial, 1 factorial, 2 factorial, 2 factorial. Now this one doesn't have the nice one for the cancellation feature of 48 like the last one did because the numbers on the bottom are much smaller than the 11 on top. So I have to write out more of it. So let's take a look. I have 11 times 10 times 9, 8, 7, 6, 5, 4, and then I can finally stop at 3 because it matches one of them on bottom. What's 1 factorial? 1. So I'm not going to write my 1 factorial of that anymore. You okay with that? What's 2 factorial? 2. 2 times 1, so it's 2. All right, so the first one, 3 factorial. I'm going to leave the 3 factorial written as 3 factorial. My 2 factorial is a 2. 1's 1. I'm not going to write it. 2 is another 2, and then another 2 factorial is 2 here. So we're going to cancel out things that match now. Certainly this 3 factorial matches. What's 2 times 2 times 2? It is 8. So all of these 2's can cancel out with that 1, 8. They will all cancel. The numerator will always have more stuff in it than the denominator does. The denominator will always completely cancel out. You will never end up with a fraction here. If you do end up with a fraction, you've made an error on something. Red flag, go back again. What is 11 times 10 times 9 times 7 times 6 times 5 times 4? Combination. And we still have that same notation where the N and the R are sort of subscript-looking things with the C in the middle. I have N items and I have R of them that I'm picking. Okay, so I'm at Sonic and I actually have 10 flavors or 20 flavors or whatever, and I'm going to choose 2 of them. And part of the reason I only choose 2 is because the Sonic's a Johnny charge for every flavor I add in. Not all Sonics do that, by the way. That's definitely a specific thing with certain ones of them. So when I'm looking at this then, I want to take this formula, and it looks at the outset like the permutation formula. I have an n factorial, and I have an n minus r factorial on bottom. The difference is that I have an additional factor on bottom of r factorial. Okay, the only difference is it's got an r factorial on bottom, which means that it's smaller, because I've got something else on the bottom that I'm playing by. Fewer choices. And that should make sense, because if the order doesn't matter, then I wouldn't count a strawberry vanilla Diet Coke and a vanilla strawberry Diet Coke as 2 drinks. Right? Yeah. All right, so here's an example now, same example before. I've got my 50 people showing you from that game, showing it doesn't matter now the order in which they're picked. Okay? Like this is Jeopardy. So I have 50 that I'm choosing from, and I'm choosing 2. I still have 50 factorial on top, and I still have 48 factorial on bottom. And the beautiful thing about the formula is that the other number on bottom is the number that I'm missing that would add up to the numerator. It's a 2. And you can either see it from your formula, it's right here, 2 right here, right? Or you can simply look at 2 numbers and say, oh, I've got 2 and I've got 48, they add up to 50. The problem works out the same way, that is, the process is the same. I have 50 times 49 times 48 factorial, and the 48 factorial on bottom cancels with those. However, I still have this 2 factorial on bottom, which is a 2 in the denominator, or 2 times 1 if you really want to write it that way. And it will reduce with something in the numerator. 50. And that 50, as Audrey said, will turn into a 25. So now you actually only have 25 times 9 instead of 50 times 9. What do you get? 1,200. Which is fewer than you had before. Before there's 2,450 ways, now there's only 1,225 ways to answer. Okay. If, this is the big if, it's not true anymore, but if all phone numbers on campus are 405-858, it's number now 585, but pretend that we were. And then we've got 4 digits at the end. The question is, how many different phone numbers would be possible? And this is another counting argument issue, but it isn't a permutation issue so much. So if you're taking a look, I have 4 different numbers here at the end, right? 4 different things that could happen in response. And you have to ask yourself whether or not, or let's see, let's talk about that one. How many different digits could go in that first spot? 10, because you could do from 0 to 9. There are 10 different digits that could go in a spot. Now, on this particular example, the phone number example, even if I select the number 2 as that first one, I can still select the number 2 as the next digit, right? So how many different options do I have in the second place? 10 more. And they're all 10s. Fundamental principle of counting, the one where we had the pizza planet example, said that how many different ways I can select each number, I find those numbers, and then I just multiply them all together. So it is 10 times 10 times 10 times 10. It is 10,000. So there are 10,000 different phone numbers that could start out 405-858. And I have 10,000 different ones. Okay. Because factorials happen when we're choosing from among 10 numbers, and we only want so many of them. Our phone number has to have 4 digits. We don't have any choices. If you only dial 4 digits at the end, it's just not so there, not anything, right? So I've actually dialed legally. So in this case, we don't have that choice of just having a numbers, but you don't have. The other thing that happens with the permutations and the combinations is that we're not repeating things, right? It's not like in theory, yes, you can go and we can order put the extra cheese on it. You can't put the extra cheese on it 3 times, right? We don't talk about it like that. In my case, maybe you could, because I don't know, probably just tell you you're being a little bit obsessive about cheese. So, but yeah, I mean, you know, you don't sort of repeat the topping. So, yeah. All right, another example. A worship team practices 8 songs on Wednesday night for the Sunday service. If minister plans to choose only 5 of the 8 that they practiced, in how many ways could they choose those songs? There's 2 different ways you could do this problem. So somebody give me an example of what you're thinking when you see this problem. Well, that's a good question. So does the order matter? So let's look back at the question. It says, in how many ways could the songs occur? Does the order matter? Yes. Because it talks about the ways that they occur. Right? If it just said how many different songs could be sung, that would be a case where it wouldn't matter. So this how many ways could they occur tells me that the order matters. So if the order matters, what kind of a problem are we looking at? A permutation. Now I'm going to do the problem 2 ways. I'm going to do it with the permutation because that's where you guys are leading me, and that's fabulous. How many do I choose from? 8. So that's the first number. And then I put a P. How many am I going to choose? 5. The formula says that I put the first number, the 8 factorial, on top. And then on bottom, I do 8 minus 5. Which is 3 factorial. So that's 8 factorial over 3 factorial. And if I write this out, it would be 8, 7, 6, 5, 4. I'll stop at 3 factorial, just enough room on my screen. With the 3 factorial at the bottom. Oh, that didn't look right. And I multiply 8 times 7 times 6 times 5 times 4. 6,720. This is one way to do the problem. Let me tell you another way. And you may think of this one, or always think of this one, you may not. Let me get this last example done and then we'll stop for the day. Okay? All right. The other possibility is to think about it like I did number 6. Right now I'm going to pick 5 songs. And I know the order matters. when I'm a music minister, I'm looking at my 8 songs I'm picking from, and I want to pick the first song. How many choices do I have for song number 1? I have 8. And if I'm not going to repeat the songs, then we kind of see that that's what sounds like what's going on. This probably seems a realistic assumption. Then after I played song number 1, how many choices do I have for song number 2? So, and song number 3, and 4, 5, and the last one is 4. And if you take a look, that's exactly the expression that I had over here, isn't it? So it's another way to think about this particular problem. So it's still 67.